It is like Konigsberg, but I am telling Konigsberg because there are two dots over O. Konigsberg bridge problem. So the Konigsberg bridge problem is actually today I can tell you and then you will understand what is the problem. So that was also very old problem. Okay, for hundreds of years, actually that was a problem. So people made fun and people tried to do that, but finally Euler solved the problems. I mean, not solved the problem, but Euler made a paper, uh, and that paper solved the problem. So everyone understood, okay, so that is why it's not possible. So the bridge problem is what? It is like there was a city like uh, there was a city like uh, Konigsberg is the name, and let me just remember. I'm not sure if I am right or wrong. So one is here, one is here, one is here also, one is here, one is here. So 1, 2, 3, 4, 5, 6, 7. 7. There were 7 bridges most probably. So how was that? If it is like that, then maybe like this. 1, 2, 3, 4, 5, 6, 7. Maybe like this. I'm not okay. Let me just do the Google search. Maybe like that. So Konigsberg bridge problem.
Yes, sir, it is like this.
It is like this. Okay. Yeah, in the left side. Okay. Yeah, I understood.
It's just
So
mirrored in the Google.
yes,
Yes, sir.
yes, yes. And now I understood. Yes. So it was like this was the like this. Okay.
Yes, sir.
So and Königsberg, Berg is B-E-B-E. Okay, that was in a place in Russia. That was in place in Russia. Okay, Berg. So if you think about A B C D, so this is the A side. Okay, this is the B side, and this is the C side, and this is the D side. Say, so there are four. Oh, okay. Another thing is you need to understand these are the water. Okay, these are the water. So I am giving you the water feeling. So the uh, okay. So I'm giving you the water feeling. Okay. So you have 7 bridges and you have A, B, C, D land. These are the land. So if you have A, B, C, D lands, and you can think about A is a point, and B is a point, and C is a point, and D is a point, and that is vertex. So AC AC, they have two, let me give the name A, B, C, and D. So AC has two lines. AC has two lines because there are two bridges. AC. BC has two bridges also. So BC has two lines like that. Is that okay? And CD has one line only. So there is one line. And AD has one line also, and BD has one line. There is one bridge. You understand the figure now.
Yes,
This is the
sir.
graph. This is the
Yes,
graph.
sir. Yes, sir.
So the problem was what? The problem was people used to play a game. People used to play a game. There, this is a city. So within the city, there is a river like this, and they play the game like who can uh, cross all the bridges only one time and then come back to the same place. So they were actually looking for the Euler graph, Euler circuit, Euler graph. So if you start from here, then maybe someone will ride the bicycle. Okay, someone will ride the bicycle, and then the bicycle they will just start, and then say in this way the person will go here and then come here and come here and then like that. So it is possible or not? That was the problem. So many young people, the students, tried to solve this, tried to do this, but nobody was successful. Nobody was successful. That is the Konigsberg bridge problem. So someday, after some time, it was very popular. It was very popular, and everyone knows. Okay, this is the Konigsberg bridge problem. Nobody can do this. I mean, cross the bridges like that. But now, if you think about the Eulerian graph theory, now you get this graph here like this. A, B, C, D are the vertices and these are the connections. So what is the degree of A? The degree of A is 3. And what is the degree of B? This is 3. And what is the degree of C? So this is 1, 2, 3, 4, 5. So it is 5. And what is the degree of D? That is also 3. So it is not possible because all the odd degrees. Okay. So if more than 2, if more than 2 odd degree vertices, so that graph cannot be solved like this. So it was not actually possible. More than 2 odd degree vertices, so it was not possible. So not it is actually not Eulerian graph and not semi-Eulerian graph, both not. Okay, not Eulerian, not semi-Eulerian. So that is why it was not possible. Is that okay? You understand what I say now? So this was the Konigsberg bridge problem, what I told you yesterday
Yes, sir.
in the last class. So now let us talk a little about Hamilton graph, and we will see established with, I mean, very serious theory or something. But the topic is here, and it comes automatically because uh, in the okay, Hamilton, it is not written like Hamiltonian. It is not Hamiltonian. It is just Hamilton graph. So the person's name is William Rowan Hamilton, and he was Sir Rowan Hamilton. Anyway, so uh, this is like in the Eulerian graph, we talked about all the edges you will cross, all the edges you will cross, and one time. And now it is all the vertices you will cross and one time. That's all. So this is the thing, and it may be multi-graph, it may be a simple graph. So uh, type of the graph can be any. There is no restriction about that. Main point is it possible to cross all the vertices only once or not? So, uh, and another thing is there is no semi-Hamilton. There is no semi-Hamilton. The point is you have to come back to the same place. So the thing is like uh, if all the vertices can be uh, crossed each for only once, okay, each for only once, whether you are crossing the edges or not does not matter. Okay, if all the vertices can be crossed uh, each for only once, then then the graph is called Hamilton graph. So in this case, you can see yes, it is possible because you start from one point, you start from one point, any point, and then you use the edge. So which edge you use does not matter. You can come here and you can come here and you can come here and then you can come here, then you can come here. So fine, you are not touching all the edges possible. You are crossing all the vertices and starting from one vertex coming back to the same vertex. So this is Hamilton graph possible. But which you can say okay, complete graph is possible. You can say cycle is possible. You understand what I'm saying? So these are the common patterns possible, but we do not find any serious type of theory so that we can call this graph is Hamilton graph or this graph is not Hamilton graph. It is not that easy like Euler. You understand what I'm saying? Sometimes you can see the graph, but you cannot be sure by seeing the graph that will it be Hamilton or not Hamilton. It's not always easy. So the people are working on that. So they have found two things. They have found two things. That means uh, uh, there will be no degree. Okay, for Hamilton graph, many researchers they have found two theory like there will be no 1 degree vertices. There will be no 1 degree vertices. So if you have 1 degree vertex in any graph, that will not be Hamilton. There will be no, there will, sorry, no, there will be no 1 degree vertices. Okay, let me write it again. There will be no 1 degree vertices. It is like one condition. So this is
Sir,
true. Yes,
like we have to come back to the first vertex always.
yes, yes. You have to come back to the first vertex always. So in that case, you can say yes. Then that will be two times. You can say that starting and ending vertex will be crossed two times.
Yes.
Is it your question?
I mean, sir, I'm saying that then, sir, if we can say it's a cycle, then we can say it's Hamilton. Like there
Yes,
should be no other. There is no other possibility. Is there? That's what I'm saying. It has to be
that is.
cycle to be
Yes,
Hamilton.
so cycle has to be included. In complete graph also you can have cycle, right? In
Yes,
complete
sir.
graph also cycle is there. So this is the thing. But uh, without any, I mean, not specific type of graph restriction. If you see any graph, okay, maybe cycle not, cycle complete, not complete, doesn't matter, any graph. So how can you say this will be Hamilton or not Hamilton? So that is a problem. Yes, cycle will be Hamilton, possible, complete graph will be Hamilton, possible. But about other things, how can you say or how can you be sure it will not be Hamilton? So there are theories, but these are not yet, I mean, confirmed about the degrees. Like Euler graph, you have the degrees. So if you think about this, I mean, sequence here, vertex or path, it will be always circuit. This is this is always a circuit. So starting ending will be same. So you can think of the circuit like you start from A, and then you go to B and then C and then D, then E, then A, like that. So that will be your circuit. So you start from A and you go in different way, possible in a different way, like, okay, this is the starting point, but you are going to B first, yeah, C first. Good. So C, then B, then E, then D, then A. Possible. So you can write, okay, another example is, the starting is A, but next vertex is C. Starting is A, next vertex is C, then B, then E, then D, then again A. So there are connections, there are edges, so that you can go in this way also. So this is Hamilton graph because Hamilton circuit is possible. These are the Hamilton circuits. These are the Hamilton circuits. So that's all. So people found something like, if you uh, see that there are no 1 degree vertex, then it may be Hamilton graph. There are degree, like each degree each degree is uh, at least at least uh, n by 2. So what is n here? n is the n is the n is the number of edges. You already know n is, oh no, n is the number of vertices. Vertices, no, n is the number of vertices. Okay. So in this case, what is the number of vertices? 5. So 5 by 2 means 2.5. So there will be no 2.5 degree possible. So there will be at least 3 degree possible. So if you have 5 points, then 5 by 2 is 2.5. Then at least 2.5 means it is actually 3, actually 3 or more. So 3 or more degrees. Now you can check what is the degree of A. So what is the degree of A? You can see in the graph. Then you can find it. The degree of A is 1, 2, 3, 4, 5. So this is 5. What is degree of B? 1, 2, 3, 4, 5. It is also 5. Degree of C, 1, 2, 3, 4. And degree of D, 1, 2, 3. And degree of E, 1, 2, 3. So you see all the degrees for the vertices are 3, 4, 5. 3, 4, 5 means at least 3. That means this is the second condition. This is the second theory. So if you think about other graph, say I'm taking another graph and it has also 5 points. So it has also 5 points, and there is something like this. Okay. So what will happen about this graph? Will it be Hamilton graph? You can say no, it will not be Hamilton graph. Why not? Because there is one vertex with 2 degree and there will be one vertex with 1 degree. So you can start from a point, but you cannot come back to the same vertex. You can start from one point, but you cannot come to the same vertex again. So this is the thing. You got my point?
Yes, sir.
But
Yes, sir.
okay, but you can have exceptions. How? Say the cycle.
Yes, sir. That's what I was gonna say.
Say the cycle. Say you have just cycle. So there are many points. Say 5 points, 6 points, 7 points, or 100 points. So it does not matter. You can start from any one point and then come back to the same point again, because this is just a cycle, nothing else. Just a cycle. So in that case, what is the degree? All the degrees are two, just two, two,
Yes,
two, two,
sir.
two. So you have 1, 2, 3, 4, 5, 6 points, and 6 by 2 is 3, but you have 2 degree, but still it is Hamilton. Still it is Hamilton because this is a cycle. So or realities, is it possible to come back to the same point or not possible? So this is the idea about Hamilton graph. That's all. Okay, so you understand the thing.
Yes, sir.
Yes, sir.
Okay, then it will be all right. No more deep uh, discussion necessary for this topic. So we will just know what is the Hamilton graph. That's it. So it's fine. So these are the 2 points. You just remember these 2 points and some examples. So fine. And now I will talk about the last thing. So today I will discuss, and uh, that is also a very simple, small thing. So we can finish this today. We can say that the syllabus is complete, or we can do some more problems tomorrow. Can I erase this now?
Okay, sir.
Okay, sir.
Sir, one thing is, sir, can you show a graph that is uh, like every degree will, there will be no 1 degree
Mhm.
vertex, but it's still not Hamilton.
Yeah, it is. You can just join these points. If you just join this, then it will be 2 degree, not 1 degree.
Yes,
But you cannot come back here. Okay.
okay, sir.
1, 2, 3, 4, 5, 6. No, it is possible.
No, sir, but like I have to cross one twice, so I don't
Oh,
think
okay,
it's
okay. Oh,
possible.
okay, okay. Yes, yes. 1 point you have to cross 1.2 times. Yes. Otherwise, not possible. Yes. Okay. So that is the understanding. That's all. So now let us go to the last topic in the syllabus, what I wanted to discuss, and it is called shortest path. Okay, shortest. This is a term actually. So you will call this shortest path of graph. So shortest path of graph means there will be uh, measurement about the uh, sequence or path. So path, you already know path means what? Path means sequence of vertices. So you can have some uh, vertices here, 5 or 6 does not matter, multi or simple does not matter. So there may be different lines and connections. Okay. So now the point is, uh, if you if you want to start from a vertex and then you go to another vertex, then you will choose a path, right? Say you want to go to a uh, to a so a to e. So this is your target. Fine. So from A to E, there are many path like, okay, let me write B or C. That will be better to understand. Let me write A to C. So if it is A to C, then you may have different path. There is no direct connection A to C. So you will go A, then D, then C, right? Or you will go A, then E, then C, possible. Or you will go, uh, what else? A, then you go to
A.
D, D, then E, then C, possible, right? There are different options, I'm saying. Yes, tell me what you wanted to say.
Sir, can't we A E D C? Can
AEDC, that is also possible. ADEC is one option, and AEDC, that is another option. Yes, that is also possible. So what I am saying, there are different paths possible to go to C from the point A. Okay, so there are many options possible, but which one will be the shortest path? Which one will be the shortest path? So if you think about A, E, D, C, that is also possible. Uh, so which one will be the shortest path? That comes that comes with the value of the age. That comes with the value of the age. So we need to think about the weightage. It is called weightage. That is how many weight you have. Weight means not only the mass or weight, what we say oজন, not only that thing. That is the value, importance, significance of the value. So weightage of every age means that can be the distance. It is also possible. If you think that A, B, C, D are the different places. So one is Dhaka, another is Kuala Lumpur, another is Paris, another is London, another is New York. So there are distance. So distance can be one consideration, okay, about the weightage. So distance is one consideration, and it is not the only one. Maybe you can think about expenses. Expenses. Okay, what is the expenses you need to incur for this? You can think about timing. Okay, how much time you need. So these are the different examples. Maybe some other examples possible. So say we have the distance in this consideration. So if you think about the distance consideration, say A to D, this line, this is say 30, this is say 30 kilometer, and CD is 40 kilometer. So you cannot say that AD is longer and CD is smaller. So it should be 20 or 15. No, in the graph theory, we do not make the graph with proportional weightage. Normally, we do not use this as a proportional weightage of the edge or any other. So if you look, maybe it seems to be longer, but it is smaller in the weight, and some another line is shorter, but it is actually more weightage carrier possible. Okay, so AD is 30 and CD is 40. So if you think about ADC, then it will be 30 plus 40. So it will be 70 kilometer path. And if you think about another one, say A to E, say this is 30 again. So in this case, it will be 30 plus 30, and no, not 30, sorry, EC I did not give. Say EC is say 35. EC means 35. Okay. So it will be 30 plus 35, and the distance will be 65 kilometer. If you think about ADEC, then what will happen? ADEC. So in this case, AD is already 30, AD is already 30, and uh, ED, I did not give any. Say ED is 10 kilometer, then it will be ED 10, and then E to C is 35. So E to C 35. So I am giving this 35. So it will be 75 kilometer. And another AE is already there 30. ED is already there 10, and DC is already there 40. So it will be different. It will be AD 30, sorry, AE 30, and then E to D is 10, and then D to C is 40. So it will be 80 kilometer total. So this is the uh, consideration. So path may be not always same according to the weightage. So according to the weightage in this example, you can say AEC is the shortest path. So fine, you will say, okay, this is the shortest path. If you want to go to the point C from the point A. So this is the concept. This is the understanding. Is that okay? Do you understand this?
Yes, sir.
So now the thing is, in this example, I have considered the distance. Distance in kilometer, it is the consideration in this example. But sometimes we can also think about other uh, dynamics, other parameter. It is like maybe expense of that path, maybe time of that path. These are the common considerations. So if you think about the places like Dhaka to Paris, Dhaka to uh, Chittagong, or Dhaka to Kuala Lumpur, so there are different places, and then expenses will be also different. Time will be also different. Not only the distance, maybe if you want to go to Dhaka to Delhi, you need to spend more than Dhaka to Kuala Lumpur. You understand what I'm saying? If you want to go to Dhaka to Delhi, then it is more expensive than plane fare than Dhaka to Kuala Lumpur. But Kuala Lumpur actually it is I mean, a more distant place than Delhi. Okay, so it is not always same that distance more and expense will be more. No, not always true. And also the time also. Time is not always true that more distance will be more time. That is also not always correct. So you understand what I'm saying? So
Yes, sir.
we will do some problems tomorrow on the shortest path, and then that will be the finishing of this chapter. A very simple thing, easy. Everyone likes this topic and understands easily and can answer correctly in the exam, so there will be no problem. That is the last topic in the graph